I'm going to be talking this afternoon about information synthesis. I'm going to give you a bit of a background on work that's been done before on text mining and literature-based discovery model. I'm going to talk a little bit about METIS, which is multi-user information extraction and information synthesis tool. And then I'm going to go into a little bit on document summarization. And hopefully these things will gel together towards this overarching theme of information synthesis. So the motivation behind my research is, put simply, massive increases in text. I'm particularly interested in scientific domains and have explored medicine and chemistry. And in medicine, which is a medline, which is a collection of abstracts from more than 5,000 biomedical journals, already has about 15 million citations. And in 2006, there were about 2,500 new citations added every workday. So clearly, this kind of quantity of information is just, you're just not able to read everything. Even the most conscientious scientist cannot get through every article that's potentially relevant to their area of inquiry. Another example in chemistry, in 1 year alone, there were more than 100,000 articles published. So again, we're in this environment where it's not the case that there's a small number of relevant articles that relate to your information need. The case is that there's hundreds or potentially hundreds of thousands of articles that relate to what you're looking for. The consequence of this is that there's connections within this set. I mean, even if you could collect everything, you can't get to implicit connections between what's in there. So my work kicks in sort of after you've got a retrieval system that retrieves those articles that are relevant to you. What kinds of tools can we build and explore to find connections between those articles or within those articles? So the underlying premise here is a shift in focus from access or retrieval and towards synthesis, trying to get within the documents and see what patterns exist within the actual text. So this notion of finding connections in text is not new. The field of text mining has several strategies to find connections or patterns in text. Clustering, taking a set of documents and putting them in groups that are most related. Categorization, which is a classic supervised learning approach where you have a set of documents with some known label, and then the goal is to derive a model so that a new document comes in and gets a correctly assigned label. Or association rules, which finds co-occurrences between words in a document typically. And there's actually products already out there on the market that label themselves as text mining tools. There's also a variety of visualization tools. I just include one here that I generated using Themescape. So this is a visual representation of the text that actually appears in the document. But I think the existing approach that most closely relates to information synthesis is this notion of literature-based discovery. So this was an idea that came about in the mid-80s. Don Swanson and Neil Smallheiser have been working on it for quite a long time. The underlying premise here is that if you search the literature, and so the original work was done in medicine, and if you search the literature on some kind of medical condition, the quintessential example that I've got here is an association between migraines and magnesium. You get all of the documents that are on this medical condition. And then you can find connections between that medical condition and the physiological reasons that underpin that condition. And so here we've got platelet activities, and these are activities in the brain, calcium channel blockers, levels of serotonin in the brain. These are all kind of the reasons why you get a migraine. They're physiological things that are associated with that particular medical condition. So this literature-based discovery model searches the literature for the condition, identifies from those documents the physiological characteristics that underpin that condition, and then does another search on those physiological conditions to see if there are things that people can do, so behavioural things that people can do, or drugs or proteins or enzymes, other kind of things that can influence these physiological conditions. So this is kind of a logical model, and the underlying premise here is that we know this connection exists. It's published, it's in the literature. We know that this connection exists. It's also published and in the literature. But we can deduce that this connection exists. Again, this was sort of the first turning point that said, you know, migraines are often associated with these 11 physiological conditions here, and magnesium seems to also be associated with these physiological conditions, so maybe magnesium is a candidate treatment for migraines. So this connection between migraines and magnesium was proposed as a new candidate treatment. And so this is the notion of discovery. It's not discovery, I'm going to find something that somebody else has written. It's discovery in the sense that this connection, this transitive connection, has not been seen before. Now, in fact, when this work was done, there were actually 2 articles that did find this association, but they were in sort of obscure magnesium journals that it was very unlikely that a physician would have read those articles when trying to figure out what kind of treatment to give somebody who had a migraine, which is a nice twist because, again, we have this situation where there's so much information that those 2 small articles were just lost amongst the hundreds and thousands and millions of documents that already exist. So why should we believe this? Well, once this candidate treatment was proposed, they then went through the traditional randomized clinical trial approach and verified that this connection was actually valid. So what appeals to me about this is that it does have this nature of discovery. But it's not actually, this connection has never actually been published before. It's new, it's a discovery. And it's a discovery that if you kind of wanted to do manually, it would be very difficult. In fact, the first system did actually have a lot of manual components, and I'll talk about that in a minute. But what's wrong with these things then? And I've told you that there's text mining systems out there. There's actually products that you can buy that call themselves text mining systems. There's been a plethora of work on the Swanson approach, which is often called the ABC model, because we go from A's to B's to C's. Well, I think there's 2 things that make me think that these solutions are somewhat unsatisfying. The first is this notion of consistency with existing work practices. How many of you, when you sit down to do a research project, the first thing that comes to mind is clustering the documents? Probably not so many. So we also have some empirical evidence that suggests that if the process that a system employs is not consistent with how users operate or think about their problem, they're probably not going to use the system. And so, I mean, we could come up with the best text mining system ever, and because it doesn't agree with how people think or how they work, it's going to sit on the shelf and never get used. We're actually working here with kinds of consequential decisions. So in medicine, for example, I mentioned that once the new idea had been proposed, it then went through a standard test of does this actually work? So this is an example where we're not dealing with questions like what movie am I going to see, where, you know, it would be nice to go to a movie that I enjoy, but the consequences of getting it wrong, you know, I might see a movie that maybe I wouldn't want to see again. Whereas here, the consequences of getting a medical treatment wrong are somewhat more severe. And so there's more likely to be multiple pieces of information that's related to this fact. There's just too much. The other piece that I think is somewhat missing is this notion of a mixed initiative approach. So the goal here is that a system will kind of do as much as it can do, and a user will do as much as it can do, and that the initiative switches between the user and the system depending on what point, what level of evidence is available. And so Herbert Simon, who's undoubtedly one of the leaders in artificial intelligence, one of the papers he wrote before he passed on was that discovery systems which solve tasks cooperatively with a domain expert are likely to have an important role. So again, the notion here is not that we're going to automate discovery. The notion is that we're going to collaboratively work with a domain expert in order to explore the possibility of results that are out there. So in terms of the talk, I mentioned I was going to talk about three things. The first is an extension to this ABC model, and it's a knowledge-based extension that I'll tell you what are some of the challenges with the ABC model, and one approach to overcome those. I'll then talk a little bit about METIS, which was the focus of my dissertation work, and which I think is actually the first step in my research anyway that tries to get at these two goals of being consistent with how scientists already work, as well as including them in the process. And then the last piece I'll talk about is multi-document summarization, and I'll tell you why I turn to different methods as we go through. So again, this is the ABC model. It's called ABC because we're going from A literature, a candidate solution, the B literature, the underlying physiological properties, and the C literature, which is the disease. And it's kind of confusing because depending on which paper you read, it'll swap ABC the other way. But the point is it's a transitive connection. The biggest challenge of this approach is this notion of a branching factor. So if we do in fact get all of the articles on migraines, at the time that Swanson did this study, there were about 2,500, I think 2,630 something. If you search for every word in every one of those 2,000 plus documents, that's a lot of words. Right? So going from here to here branches out. Then if you search for all of those words, you branch out again and you get this extraordinary number of terms. So the challenge here is, how do we get the ones we want to find, but at the same time don't get all of this extra stuff that's not going to lead us to a promising solution? So, good thing to ask is, how did Swanson do this? Right, the first paper that did this, he referred to removing redundancies and non-useful terms. So he got all the documents for migraines, found all the B terms, and then removed redundancies. And so the original number of words was about 14,000, and he reduced them down to about 2,700. I'm sorry, with no pruning. But then manual pruning, the list dropped down to about 150 to 200. So this was a manual process. He sat there and went, B term, no good. B term, no good. B term, no, still no good. So if you actually sort of figure this out, there's about 90% of those B terms were pruned manually. Right? They were he was getting rid of that branching factor by manually getting rid of stuff. And so this is probably not going to scale very well, right? 90% pretty manually, not the best approach. Also mean that it's revealed that there are these transitive connections, but probably not going to scale well. So one approach to try and extend this is to explore different representations of the text. So instead of just looking at word co-occurrences, we're going to change the representation so that we're looking at concepts. And concepts in this model, or a semantic representation in this world, is this notion of trying to unify synonymy in text. And it's a very difficult problem because things being exactly the same is sort of a slippery slope. I've listed here some synonyms, so serotonin is the same as 5-HT and some other examples here. What we want to do is every time we see one of these in the text, we want to reduce that to the one concept. And we're going to give it a unique ID, and that's going to be the concept. And every time we see any of these phrases, we're going to say, okay, chalk one up to that single concept. The other piece to extend this is there's kind of a logical connection in the ABC model, and that is we know, or if you start with the Swanson's paper, the kinds of B links are physiological things. So because we know that they're physiological aspects, then we should be able to know ahead of time what kinds of things would make sense as B terms and what kinds of things would make sense as A terms. And so we actually tapped into a knowledge source and used semantic types in order to make sure that the concepts that we were getting at each of those points were actually of a valid semantic type. So we used the Unified Medical Language System, which is a knowledge resource by the National Library of Medicine. Very extensive, has millions of concepts. This is actually somewhat out of date because this is the 2004 version, and obviously it's 2007, so there are more concepts now. The important thing that sort of this project tapped into was this notion of the semantic types and the semantic network. And again, this was looking ahead at time of what sorts of things make sense at each of these intermediate stages and making sure that you only kept information that was related to those. So in terms of methodology, we evaluated this by looking at the migraine-magnesium connection that I've used in this example so far. We collected all of the migraine citations, and we did this in a way that it was the same as the citations that Swanson would have had available to him had we done the study back in 1988. We then just wanted to generate alternative representations. We played with word representation, the concept representation, and then this semantically pruned concept representation. So this set here was a subset of the concepts. And to evaluate, we kind of took the migraine magnesium connection as just one example, and we just wanted to be able to replicate that. Now, in terms of the methodology, it's actually the most common approach to evaluate these kinds of tools, but just so you know, it has one drawback, and that is we could tell you when we find what he found, but then we have all of these other connections, and we don't have the information about whether they were, in fact, valid connections or invalid connections. And that's, I think, I mention this because these discovery systems are very difficult to evaluate. You have a double-edged sword. On the one hand, you want to come up with new things that nobody has ever seen before. And on the other hand, if you don't come up with anything that somebody's seen before, it's unlikely that folks are going to actually believe that your system is valid. So evaluating discovery systems is a very difficult task. This is a common approach, but it could definitely do with some more work. So how do we do then? I'm going to jump over, what the heck, I'll spend some more time. So the word representation is probably the most common choice. Typically stop words are removed, so these are words that have low information content. You know, the, a, in, is. In addition to a set of generic stop words, don't know that I got from here, I also added some medical stop words. So these are words that appear frequently in a medical abstract, but again, they don't have much information. For the concept representation, I went through the process of mapping the abstracts mapping the titles to UMLS concepts. There are actually more resources available today that do this for you, but the approach that I used was partitioning the title sentence into phrases based on stop words, and then for each of those phrases, trying to see if there was a direct match in the UMLS. If there wasn't a direct match, then I went through the process of doing an approximate match, which was changing words around as well as using stemming. And then lastly, I selected the best concept. For the semantically pruned concepts, I looked through these semantic types And these semantic types are kind of cool because they're organised in a hierarchy. And so ahead of time, I knew what I wanted the B terms to look like. I knew what I wanted the A terms to look like. And I deliberately tried to select semantic types that would give me the kinds of concepts that I thought would be of value. And so I ended up using only 37 of the 134 semantic types. And again, just so that it's clear, I did this ahead of time and I knew what kind of things I was looking for. So if you were looking for a different kind of connection, then this step would need to be resolved. And since then, this area has been explored in other systems that do actually allow a user to say which semantic type they want at each level. In terms of evaluation, using the standard precision and recall measures, so the 11 physiological condition that Swanson identified were our gold standard. So precision was the number of relevant B terms that were retrieved using either the word, the concept, or the pruned approach, divided by the number of those levels returned. And then recall was sort of how many of those 11 did you actually get back. Now this was actually using the total number of relevant titles, and then the second kind of evaluation was actually looking at seeing whether you could actually get those 11 physiological connections back. And I mean, going back to how Swanson did this, remember he pruned 90 to 94% of the actual connections. Well, folks probably aren't going to be interested in reading through, 2, 4, 5,000 words. So we did this at 20 terms, again, words, concepts, or semantically pruned concepts, and again at 50, to see how many we would actually retrieve. And then lastly, we looked at the how much would this actually reduce the space that you're searching in. Again, folks don't have hour after hour to actually prune pieces, so we wanted that to be more efficient. So this shows you the precision and recall curve. And so again, precision is of the things that are returned, we want them to be correct. And recall is of all the things that exist, we want the system to get everything back. And of course they trade off each other, so you have to measure both. You can see here that for low recall, we get very good precision. So this is telling us that if we use these semantically pruned concepts, the things that come back are likely to be correct. And you can see a pretty drastic difference between the semantically pruned concepts and the medical word concepts. You can also see here that the words, which really, the medical concepts were able to retrieve more information than the semantically pruned approach. So what this is telling you is that if you've got a short amount of time and you want the list that you're looking at to be correct, then the semantic pruning is going to be the right choice for you. But if you're wanting to make sure that you get every single connection out there, then maybe you want to use a medical concept representation instead. In terms of the number of links, again, the gold standard here is Swanson's migraine to magnesium link. Most people look at the first page, which is sort of the first 10 links. We were a little bit more loose and said, okay, well, let's say they look at the first 2 pages, or they're really keen and they're looking at the first 5 pages. If they were to do that, would they get back the links that Swanson found? Using a word representation, they were only able to find 3 of the 4 links. Using a semantically pruned representation, they were able to find 9 out of these 11 links. Now this, as I mentioned, doesn't address the issue of the other ones that were in that set, how many of them were actually true or false. We don't know. We also looked at the dimensionality reduction and found that for a word representation, For each citation, there was likely to be about 4 words. For the concept, about 2. And for a semantically pruned concept, about less than 1. So we really pruned drastically. Now this was all done for titles so that we could compare it with Swanson. But we also looked at, well, what would this look like in terms of abstracts? And you can see that the dimensionality reduction here is enormous. Why does this matter? Well, our motivation here was this pruning factor, right? For each medical concept, there's hundreds of physiological things, and then thousands of potential treatments associated with each of those physiological causes. So this dimensionality reduction is pretty neat because it tells us that even though there's fewer, we're still finding this connection that we know is important. So this has really important implications in terms of scaling this up to diseases like, say, breast cancer, where instead of the 2,500 migraine articles, you now have 120,000 articles just on breast cancer. So this is much more important when you have those, when you have more articles. So what have we learned so far? From the ABC model, we learned that maybe this concept representation, there's something to it. Compared to a word representation, it improved precision and recall. And we found more of the 11 connections in the top 50 big terms. The semantic pruning, it improved precision, but it came at a cost. Our recall was degraded. But we still found more of the 11 connections that Swanson found. So, are we done? Well, So we've just finished talking about the ABC model and how a knowledge-based representation might allow us to deal with this branching factor. We're going to try and switch gears now, and we're going to talk a little bit about an alternative approach. It's embodied in a system called METIS, and the main difference here is that it's motivated by how scientists already synthesize evidence from literature. So our goal here is, we're still sort of in this ABC framework, but we're looking at one of these connections, and we're trying to figure out how do scientists accurately quantify what that connection really is. So we want to insert something in here, zooming right in, and that's where we're going to spend a bit of time in METIS. We're still being motivated by our 2 original premises here. And we're really focusing on trying to be consistent with the existing work practices. We also start to get into more of an interactive model, but the main emphasis is looking at how scientists already work. And evidence-based medicine provided much of the motivation behind this approach. So in evidence-based medicine, the goal is, given a set of studies, say that all explore treatment strategies, we want to know which of those studies is actually which of those treatments rather is actually the right approach. Or if we're looking in an epidemiology framework, we want to know what risk factors are more associated with a particular disease so that we can change our behaviours and hopefully prevent a particular disease. An important piece about evidence-based medicine is that you have to define the research question in advance. So this is a model. So I actually spent some time, I should go back. I actually spent some time looking at scientists and studying how they synthesize evidence from literature. I looked at 2 groups, a group in complementary and alternative medicine, which was a prospective study. So I had this really nice opportunity. They were just starting to do the study, and so I was involved in their meetings as they did that. I then was actually located at a group in public health where I became part of the group. But this was a retrospective study in the sense that they'd already done the study that was the main part of my research. They were doing other studies that also were systematic reviews, but they weren't the main area of my research. What came from that was this model of manual synthesis. So in this approach, you start with some kind of, I've called it a hypothesis projection. So it's sort of, you know kind of what you're looking at, but it's not a research question because it may evolve over time. And in fact, in looking at these folks, their research questions did evolve over time because there wasn't enough information to actually answer their original question. So from this hypothesis projection, this gamut of possible research questions that you're going to answer, you then go through a process of retrieving documents, selecting documents. This process is explicit in a meta-analysis. You actually say in your document, I searched these databases using this query, and these were the documents that were retrieved. This gives you a collection of documents. You usually, so there's inclusion and exclusion criteria, again, are made explicit in the actual document. You extract information from those documents. Depending on what your study is, the information will change, but the information seems to fall into one of four categories. Information about the population, so what were their gender, where were they from, how old they were. Information about the actual study design, how many people were in the study, when was the study conducted. Information about the disease, so what grade or how severe were the subjects suffering from the disease of study. And information about the risk factor, if you're dealing with an epidemiology kind of meta-analysis, or the treatment strategy if you're dealing with a medical situation. So depending on what kind of study will vary the information extracted, but the information about the population and the study seem to generalize fairly well. Once you've extracted the facts, you then verify the information. Now remember, one of our goals in information synthesis is to be consistent with how scientists already do this. The scientists I studied, particularly in the complementary and alternative medicine group, were very well recognized scientists. This verification process they went through. Right? So this is not because you're just learning how to do this. This is a part